In the last webcast, we saw that mutarotation could be explained either by reversible ring opening and closing or by the formation of a cyclic, resonance-stabilized cation called the oxocarbenium ion. We'll focus on the oxocarbenium intermediate in this webcast. The first thing to notice about this ion is that it is stabilized by resonance. In fact, it's the only stabilized cation that forms in sugars. This is why we typically focus on the anomeric carbon as the center of electrophilic reactivity in sugars. It's the only position where a cation may be reasonably placed. Reactions at this carbon will typically involve the attack of nucleophiles in either nucleophilic association or nucleophilic addition elementary steps. Transformations of monosaccharides that strongly suggest the intermediacy of an oxocarbenium ion usually involve treatment of the sugar with a weak nucleophile under acidic conditions, for reasons that you'll see shortly. Most generally, you can think of these reactions as SN1 substitutions at the anomeric carbon. Mutarotation involves the approach of a molecule of water to either diastereotopic face of the oxocarbenium ion. However, if we place the sugar in some different nucleophilic solvent, association of the solvent could occur to generate a new molecule entirely. After the loss of a proton, the resulting neutral product has lost the anomeric hydroxyl group and now possesses a new bond between the nucleophilic atom and the anomeric carbon. When the solvent is an alcohol, the nucleophilic atom is oxygen, and we call the reaction acetal or ketal exchange. You'll notice the presence of an acetal functional group at the anomeric carbon now. Amines can also participate in this reaction as nucleophiles. Notice that only the anomeric hydroxyl group is displaced. This observation strongly supports the intermediacy of a stabilized cation. It's important for us to consider the stereochemistry of this addition step because the carbon of an oxocarbenium ion in sugars is always prochiral. Just like mutarotation, acetal exchange and related SN1 reactions will produce a mixture of diastereomers, depending on the relative amounts of alpha and beta face attack on the oxocarbenium ion.